Okay. So, before I start, I'll remind you that, and I mean, I'll be posting another announcement when I have office hours later today. But so your first exam is due tonight. I'd also changed your second homework to also be due tonight if you needed the extra time and to talk during office hours. So, like I said, I'll remind you all about that. So, last time I had finished with this property that allowed you to deal with congruences. So, for instance, so there was this fact, I should say, that if, so we'll say A, B, C, D, and M are integers. M is positive. Then if A is congruent to B mod M and C is congruent to D mod M, then you had a couple of things. So one, A plus C is congruent to B plus D mod M. So you can add those two congruences in a way that you would add equations. Similarly, you could subtract the two congruences. So A minus C is congruent to B minus D mod M. And another is A times C is congruent to B times D mod M. Okay. And so this is telling you that it appears that dealing with congruences is very similar to how you dealt with equations. It's just that this equality signs replaces congruences. So as I noted last time, or I called your attention to, note no rule for division is listed here. Okay, in fact, calling attention to this, so in fact, here's an example. Well, notice that 20, okay, is actually congruent to 12 mod 12. Okay. Sorry, it's not congruent to 12 mod 12. What am I saying? 20 is congruent to 8 mod 12. Here, I'm going to redo that. So 20 is congruent to 8 mod 12. If 20 were congruent to 12 mod 12, it would be divisible by 12. It would be congruent to 0 mod 12. So 20 is congruent to 8 mod 12. I can see this just by noting that, well, if I divide 20 by 12 versus 8 by 12, I'm going to get the same remainder, which is 8. And so 20 is congruent to 8 mod 12. But 20 is 4 times 5. Right, so this is 4 times 5 is congruent to 4 times 2 mod 12. Right? But 5 is not congruent to 2 mod 12. Okay. So 4 times 5 is congruent to 4 times 2 mod 12. But trying to divide by 4 here to leave myself with 5 on the left and 2 on the right doesn't work because 5 and 2 aren't congruent mod 12. Okay. So I can't divide in this way. Now, it turns out that I can actually divide in a special case, but in this case, I can't do it. And what is the problem? The problem is, you might have guessed, the relationship between 4 and 12. The problem is that 4 divides 12. 4 divides this modulus, and it turns out that that is an issue that prevents this very thing. Okay. So it turns out, for instance, that if 4 and 12 were relatively prime, I could actually do this. So I'm going to stop now because I'm getting ahead of myself, and I'll talk about that in a little bit. But the point is to say that I can do these normal operations that I would be able to do for equations, but I can't divide in this way. Okay, so this is also telling you, I'm again getting ahead of myself, but since I've already spilled the beans and said that this division actually works, so this division actually works whenever the thing that you want to divide by is actually relatively prime to the modulus. Then if the modulus itself is prime, right, so if you're considering congruence as mod p, where p is a prime, then dividing by a thing, right, is always going to be possible, because anything you choose is always going to be relatively prime to that prime. Now, you might stop yourself and say, wait, what if you choose a multiple of that prime, right? If you choose a multiple of the prime, then that's not going to be relatively prime to p. But it's not a problem, because a multiple of that prime is going to be 0 mod p. And we don't care about dividing by 0. In fact, even with normal numbers, we know we can't divide by 0. So any multiple of p would be 0. We don't talk about dividing by 0. But anything that's not a multiple of p is going to be relatively prime to p. So anything other than a multiple of p I can divide by, right? So anything other than 0 I can divide by. Okay, and some of you may already know where I'm going with that. But anyway, I'll get to that stuff a bit later. But the point is that for these other 3 operations, so for adding congruences, subtracting congruences, multiplying congruences, I have this fact. Okay, this is nice because it lets me do things that otherwise are kind of nasty computations. So for instance, here's another quick example. We'll use number 3 here to do a computation that would be easy. So let's look at what 7 squared is mod 6, we'll say. So 7 squared is 7 times 7 mod 6. Okay. So, of course, I could just do this multiplication. I could say 7 times 7, that's 49, and then I could just see what that is mod 6. That's perfectly fine. But I'm going to show in a second why doing it the way I'm about to do it is much better. Before I begin here, though, the thing that I could note is, but 7 is actually congruent to 1 mod 6. Right? And so I can use 3 here and the fact that I have this congruence to say that 7 squared is congruent to 7 times 7 But by number 3 here, this is congruent to 1 times 1. And 1 times 1 is 1, so this is congruent to 1 mod 6. Okay. Now, as I mentioned, I could have just said 7 squared is congruent to 49 mod 6. But 49 mod 6, well, 48 is a multiple of 6. So I could have just said 49 itself is congruent to 1 mod 6 and been done, right? So you're probably asking me, well, what's the point of doing it this way? If I could just, not using any tricks or any further knowledge, I could just use the definition of modular arithmetic here to say, well, I know that 6 goes into 48 evenly, so I have 1 extra left over, right? I got a remainder of 1 here, so it's congruent to 1 mod 6. Well, I could have also said compute, say, 7 to the 500 mod 6, right? And 7 to the 500 is a lot harder to deal with. But using property 3, 7 to the 500 is really 1 mod 6. Right? Okay. So, it turns out that modular arithmetic in this way can allow you to very, very conveniently compute powers, really, really large and awkward powers of numbers. And that's one of its strengths. This is actually going to be particularly powerful for us when we start talking about cryptographic applications of this stuff. Okay. So one more thing I will say. So in fact, it's kind of important. In fact, I'll dedicate a whole section to it here a little bit later. So fact, computing large powers mod m is important and made easier than actually computing them normally, right? So the computations involved are a lot nicer. Okay. So quick corollary to those rules is the following. So as a corollary to those rules and the following, if A is congruent to B mod m, then A to the n is congruent to B to the n mod m for any positive integer n. All right. So the proof of that is really quick, and this would work regardless of what these numbers were. You could view our example that we did earlier as kind of showing you what it is that's going on here. So since A is congruent to B mod m, using 3 in the previous proposition, means that A squared is congruent to B squared mod m. Okay. So keep multiplying. You keep multiplying until you get n. Oh, that's a b. Okay. All right. So, being able to compute powers mod m, where the powers are potentially really huge, this is very important for some of the applications that we're going to talk about. So here's an example of a famous near-miss solution to the equation involved, or rather one of the equations for some n involved in Fermat's last theorem. So it's the following. Check does 3,987 to the 12 plus 4,365 to the 12 equal 4,472 to the 12. Okay. Now, you may have already noticed, well, if it did, then Fermat's last theorem would be false, and said previously that Fermat's last theorem was proven in the 90s, so the answer is no. But to actually check this is hard. So no, but checking can be difficult. Checking to make sure can be difficult. Right, because the numbers involved are big enough that raising them to the 12th power is rough. Okay, that's a tough thing. Okay, so if this equality holds, then both the left-hand side and right-hand side, since they're equal, they must be congruent mod m for any m. Right? Then left-hand side is congruent to right-hand side mod m for any choice of m here, right? For any choice of m that's positive. So think about that for a second. This is nothing deep. I don't need a statement or theorem or proposition to say this. This is saying that if you have two positive integers and they are actually equal to one another, right, then they should be congruent mod m regardless of what m is. That's just saying that if you take those two positive integers, right, which are equal, which means they're the same positive integer, and you choose to divide it by m, the remainder should always be the same. That's true, right? That's clearly true. So this is not a big thing that you're saying here, but this is a subtle thing you can say to help you use modular arithmetic to check whether or not two integer quantities are equal to each other. So try m equals 10. Okay, why might we try mod 10 here? Well, as we saw in an example last time, mod 10, looking at an integer mod 10 is just looking at its last digit. So note that 3,987 is congruent to 7 mod 10. Again, remember, mod 10 is peeling off the final digit. It's peeling off the last digit because you look at this thing and you say 3,987, that's 3,980, which is divisible by 10, plus 7, right? Okay. So 4,365 is congruent to 5 mod 10. Okay. And lastly, the right-hand side, 4,472 is congruent to 2 mod 10. Okay. So, note that I actually have to, there's no trickery here. I'm actually just going to do this by hand. So what is 7 to the 4th? So 7 to the 4th is 7 cubed is 343 times 7. So that's 2401. Right, so this is congruent to, it's actually equal to 2401, which is congruent to 1 mod 10. Okay. And so what do I do here? I cube this, right? Thus 7 to the 12th. What am I doing here? I'm saying 3,987 is congruent to 7 mod 10. So now I'm going to do my computations with 7 since I want to raise this thing to the 12th power. So 7 to the 12th is the same thing as 7 to the 4th cubed. Okay, but cubing this thing, this is just 1 cube since this is congruent to 1 mod 10. So this is just 1 cube, so that's just congruent to 1 mod 10. So thus, 3,987 to the 12th is congruent to 7 to the 12th, which is congruent to 1 mod 10. I guess that's one thing I could say. Another thing I could say here is this is the same as saying that the last digit of 3,987 to the 12th is 1. Right? So this statement is the same thing as saying that if I actually do this exponentiation, 3,987 to the 12th, what is the last digit of that? It turns out it's 1. Okay. Because remember, the last digit of a number like this is just whatever its least non-negative residue is mod 10. So in this case, it's 1. So its last digit is 1. So in fact, this is the first example of one of these types of problems that you'll hear about in number theory. These are little tricks where you're given some ridiculous integer in an expression. Usually it's an exponential thing, so you're given some ridiculous integer, and then you're asked, what's the last digit of this thing? Okay. You're asked, like, what's the last digit of this thing? What's the last 2 digits of this thing? These are the sorts of things that you could be asked about some absolutely massive integer expression. So this is one of the ways in which you can answer. So anyway, 3,987 to the 12th is congruent to 1 mod 10. Okay. So continuing on. Actually, let me keep that handy because I'm going to refer to that. So this is my example continued here. So 4,365, so 3,987 is congruent to 7 mod 10, and I used powers of 7. So I wanted to see what 7 to the 12 was, and I did. It was 1. So now I want to see what 5 to the 12 is. Well, note that 5 to the n always has 5 as its last digit. Right? So that's easy enough. No thought had to be put into that. 5 to the n always has 5 as its last digit, and so 4,365 to the 12 is congruent to 5 to the 12, which is congruent to 5 mod 10. Okay. Again, this is equivalent to saying that the final digit of, right, the last digit of 4,365 to the 12 is 5. You would have been able to see that, though, again, for the same reason. This is some basic divisibility properties of 5 here. Okay. And then lastly, note further that 4,472 to the 12th is congruent to 2 to the 12th. I can actually compute that, right? 2 to the 12th, that's might not be one that you have off the top of your head, but this is 4,096. 2 to the 12th is 4,096, which of course is congruent to 6 mod 10. Thus, notice that 3,987 to the 12th plus 4,365 to the 12th. So this was congruent to 1 mod 10. This is congruent to 6 mod 10. So, 5 mod 10. So this is congruent to 1 plus 5 mod 10. So that's congruent to 6 mod 10. But that means that it's congruent to 4,472 to the 12th mod 10. Because it's also congruent to 6. So mod 10, these quantities seem to agree. Well, they don't quite seem to agree for mod 10. They do agree mod 10. Okay. So, it's a little bit of evidence that maybe they're equal. Of course, we're spoiling ourselves here because we don't actually, we already know that they can't be equal. So we know that this has to fail for some m. Okay. And so we check m equals 9. Right, check the mod 9 case. Okay. Now, mod 9 is not quite as easy to check as mod 10. Mod 10 is just peeling off the last digit. And you might think for a second, we'll show this in a section here in a little bit. But right now, what do you do when you are considering some positive integer mod 9? Well, mod 9 is, whereas mod 10 was just the last digit, mod 9, one thing you can say is that an integer mod 9 is congruent to the sum of its digits mod 9. Okay, and this you might recall being involved with divisibility rules. So the divisibility rule for both 3 and 9 were very similar. If a number was divisible by 9, the sum of its digits was divisible by 9. Okay, so it turns out that that does it. That's enough. There's actually an easier way to see this, just looking at its base 10 expansion. So this uses the fact that we use base 10, 9 is one less than the base, so this actually would be a divisibility rule in any number base for whatever number was right below the base you're using. So if you're computing in base 7, this would be a divisibility rule mod 6, okay, in that number system. So anyway, so again, getting ahead of myself a little bit. Note, it's also Maybe I'll say this before going on. So they seem to agree. In fact, if you check using a calculator that displays, I think the textbook says it displays 10 places, then both quantities display the same exact amount. So display the same thing. So it really looks like they're equal. Okay. So then checking when m is equal, or when m is equal to 9, then 3,987 is congruent to what mod 9? So this is 3 plus 9 plus 8 plus 7. So that's 12 plus 15. So that's 27. Mod 9, that is 0. If you're confused about that, I'm going to go over this later. But right now, you can just think what I'm doing is I'm summing the digits and seeing what those are congruent to mod 9. Okay? So 3,987, if you sum those digits, you get 27, which is 0 mod 9. It's divisible by 9. Okay. 4,365 is congruent to, so 4 plus 3, that's 7, plus 6, 13, plus 5 is 18. That's also 0 mod 9. Right, 18 is divisible by 9. And then lastly, 4,472 is congruent. So 7 plus 2 is 9, plus 4 plus 4, so 17. That is congruent to 8 mod 9. Okay. All right. Now, note, this is something that is done frequently. I'm computing mod 9. I'm doing stuff mod 9. 8 is like the biggest a digit can be mod 9, right? If you're thinking of number bases, then the biggest digit you can have base 9 is 8, right? That's as big as a digit can be. And of course, the larger a digit is in general, the more complicated it is to actually compute with it. So you can use the thing that it's not the least non-negative residue, but it is an equivalent thing that is easier to deal with. So in this case, 8 is congruent to minus 1 mod 9. So 4,472 to the 12 is congruent to 8 mod 9, which is congruent to minus 1, or sorry, 8 to the 12th, I should say, which is congruent to minus 1 to the 12th mod 9, which is congruent to 1. Now, why would I switch over to minus 1? Because it's easier to deal with than 8. Okay. Okay. But these are both 0, so 3,987 to the 12th plus 4,365 to the 12th. They're both congruent to 0 to the 12th plus 0 to the 12th. So that's 0 plus 0, which is 0. And that is not congruent to 1 mod 9, but 1 is congruent to 4,472 to the 12th. So we have found some m for which these two quantities are not congruent. Okay. Thus, 3,987 to the 12th plus 4,365 to the 12th. This is not equal to 4,472 to the 12th. But it's close. Okay. I actually don't know exactly how close they are. Like I said, they at least display the first the same, like to 10 places. If you're looking at a calculator, they display the same, but I'm not actually sure exactly how close they are. Okay. All right. So, I want to return to this discussion about division. Okay. So next, I want to return to this discussion about division. So what I want to say here is this following proposition. So if AC is congruent to BC mod M, and the GCD of C and M is 1, then A is congruent to B mod M. Okay, so this is exactly my division rule for congruences. Unfortunately, I have to have this. This is as good as I can do if M stays the same. Okay, so the very next proposition, you'll see why I'm saying M staying the same here, as if there was even an option. Okay, but this is as good as I can do for a division rule to supplement those other rules for dealing with congruences. So, how does this work? So I can do this proof by recasting my congruences in terms of divisibility, right? So I just think about divisibility here. So AC congruent to BC mod M. That actually implies that by definition, M divides the difference AC minus BC. Right, that's what it means. Of course, I can factor this, so this means that M divides C times A minus B. You understand what's about to happen now. But the GCD of C and M is 1, thus M dividing C times A minus B. So M divides a product, C times something, but M and C have GCD 1. So if M divides product, C times something, then M must divide the something. It must divide A minus B. Hold on just a second. One of my cats is making a bunch of racket. Okay. So if GCD of C and M is 1, then since M divides this product, it actually just has to divide the other thing, A minus B. It can't divide C. So the only contribution here to divisibility has to come from the other thing, right? This is one of those early chapter 2 propositions. So M divides A minus B. But if M divides A minus B, then in terms of congruences, this is saying that A is congruent to B mod M. And that's exactly what I wanted to say. Okay. Okay, so that's my divisibility rule. Now, it turns out that if I want to divide an expression in congruences, but I don't have this fact, the thing I want to divide by is not relatively prime to the modulus, then I'm not totally doomed. There is something I can do. The only problem is that this moves me out of mod M. Okay, it moves me out of mod M. So what do I mean by that? So there's the following proposition. If AC is congruent to BC mod M, okay, and the GCD of C and M is D. So not 1, it's some D. Then, if I want to go ahead and divide by C, I can totally do that. But what happens is A is congruent to B mod M over D. Okay. And, of course, another way of writing this is A is congruent to B plus M over D K mod M with K between 0 and D minus 1. Okay. Okay, so the proof of this is actually really easy. So if AC is congruent to BC mod M, okay, then as in the previous proposition, M divides AC minus BC, which implies, as before, M divides C times A minus B. And from this expression, M over D divides C over D times A minus B. But since D is the GCD of M over D and C over D, what is the GCD of C over D, M over D? Sorry, so if D is the GCD of M and C, I should say, sorry, then what is the GCD of C over D and M over D? Well, this is 1, right? This is one of those earlier propositions. If you consider a pair of integers, consider their GCD, call it D. Then if you take each of those and divide by D, they are now relatively prime, right? So taking a pair of integers, dividing them by their GCD yields a pair of relatively prime integers. Okay, so GCD of C over D and M over D is 1. So this means that M over D must divide A minus B, and so A is congruent to B mod M over D. No, I didn't put the parentheses here. That's fine. Okay, the rest is just a statement that you're just doing the division algorithm here with remainder. So and this is what you get, right? So your A is congruent to B, the remainder is some multiple of M over D. So anyway, that's it. That's the rest is straightforward. Okay. So here's a way that we can use some of this stuff. So the textbook goes through a number of examples that show how these things can go. So firstly, I'm going to call these examples. Okay, so first example, let's say that 3C is congruent to 12 mod 5. And I want to solve for C. Okay, well, I can divide both sides by 3 here. Why can I just divide both sides by 3? Because 3 and 5 are relatively prime. So this implies that C is congruent to 4 mod 5. And I can divide by 3 since GCD of 3 and 5 is 1. Okay. All right, so quick note here. Since in the remaining examples, I'm going to flip-flop between these notions. So, as was mentioned in this proposition that was immediately prior to this example, sometimes if I really, really want to divide, but I don't have this fact that the thing I want to divide by and the modulus are relatively prime, but I still want to divide, then that changes in the expression that I get after doing that division. That actually changes what the modulus is, because you divide the modulus by d, right? And so I leave the world of what I started with, right? So I leave the modular arithmetic world and I go to the modular arithmetic world with a different modulus. Or maybe in one of these problems I go from modular arithmetic world to integer world. Okay, so the question is, if I ask you for a solution to a modular equation, what do I mean? The convention that we'll use is you always give the solution in the same world. Okay, so we always stick to the original world in which the equation to be solved is stated when writing the solution. And I'll show you an example. So even if we have to pass through other worlds, we always state our solution in terms of the original problem statement. Okay. This is similar to, plenty of things you've seen before, right? When you do various types of substitution that you've done in the past, you typically, at the end, you get some expression. It might be nice in the substitution you've done, but you have to substitute back in for something else. So anyway, in the modular arithmetic world, the reason it's nice is if you have an equation in modular arithmetic and congruences, then necessarily, because there's infinitely many integers that would satisfy ultimately your congruence. So like if you, for instance, in this case, right, if you start out with this equation, 3c is equal to 12 mod 5, divide by 3 because you can here, so c is congruent to 4 mod 5. So the solution to this congruence is c is congruent to 4 mod 5, so any integer c that is congruent to 4 mod 5 solves this relationship. But how many integers are congruent to 4 mod 5? Well, infinitely many, right? Take 4 and start adding and subtracting multiples of 5 from it, right? And you get infinitely many integers are congruent to 4 mod 5. So the solution to this yields an infinite string of integers for various reasons, right? We're typically happier to write it like this just because it's a nice, more abbreviated form. Okay, so here's a second example. We'll say 10c is congruent to 30 mod 7. Okay. This implies that c is congruent to 3 mod 7 since 10 and 7 are relatively prime. Okay, so it works out exactly as before. Okay, let's do an example where it doesn't quite work out in the same way. So what about 2c is congruent to 7 mod 9? So note that division is kind of awkward here because when I try to divide, well, 7's not divisible by 2. So even though 2 and 9 are relatively prime, dividing here, just stupidly, I would have c is congruent to 7/2 mod 9. That doesn't make any sense. So this is not what I want to do. So then what's the idea here? The idea is that adding multiples of 9 to either side is the same as adding 0, right? So when dealing with equations and coming up with creative ways to add 0, right? So adding a minus a to both sides, right? Plus a minus a is a typical algebraic trick. Here, another way of doing that is any multiple of 9 I add is like adding 0. So it's like I did nothing here. And so 2c is congruent to 7 mod 9 implies, for instance, that 2c is congruent to 7 plus 9 mod 9. So actually 2c is congruent to 16 mod 9. Okay. So now we have something that makes sense to divide by 2. And now this implies that c is congruent to 8 mod 9. Again, I can do this division since GCD of 2 and 9 is 1. Okay. Now, I'm not guaranteed that after adding a single copy of 9, I get something that makes sense here necessarily. Maybe I have to add some other multiple of 9, but in this case, just adding 9 works. Okay. So this is something that you can do in congruences, right? You can add something that might not be thought of, immediately as being the same as adding 0, but it is because you're dealing with congruence mod 9. Okay. Okay, so let's continue on. Let's do another example. So here is another example. Let's try to solve 6c is congruent to 18 mod 21. Now, you'd like to be able to just immediately divide both sides of this by 6, since 18 is nice and divisible by 6. But notice that you can't do that, since the GCD of 6 and 21 is not 1, right? It's 3. So GCD of 6 and 21 is 3, so I can't just divide. Or can I? Right? Well, I can't just divide and keep my modulus the same, but referring back to this proposition that I proved earlier, if I'm willing to let my modulus change a little bit, then I definitely can divide, right? It's just that I get a congruence mod some different thing. I get mod m over d instead of mod m. So let's see what that takes us. We want to solve this congruence mod 21, but let's just go ahead and do this division. So I want to divide by 3, right? So I want to divide the modulus by 3 here. So I am still going to get a is congruent to b mod, maybe I'll put that proposition back. So here. So if a times c is congruent to b times c, so in fact, in this case, c is 6, so c is 6 here. And if I want to divide by 6, I need to divide my modulus by d, where d is the GCD of 6 and m. Okay, and so by the previous proposition, C is congruent to 3 mod 7, right? Because 21 divided by 3 is 7. Okay. So C is congruent to 3 mod 7. Now that's certainly a statement in the mod 7 world, but that's not what I was originally asked. I was asked to solve this in the mod 21 world. So what do I do here? So I get a list. I get C is congruent to 3. Now, in the mod 7 world, that's all I have. But in the mod 21 world, what's another thing? What is something mod 21 that is congruent to 3 mod 7 that is still less than 21? Well, 10. All right, so this is definitely distinct mod 21. Mod 7, 10 and 3 are the same, but mod 21, they're not. They're different. Furthermore, what's another example? What's another integer that is the same as 10 and 3 mod 7, but is not mod 21? I just add 7 again. This is 17. So C is congruent to 3, 10, and 17 mod 21. So this is the list of solutions mod 21. All right. So mod 7, I have a single solution. But it turns out that these three things, which are different, they're distinct integers, mod 21. So they are distinct classes, right? They are representatives from distinct congruence classes. And all these things, while they're the same, mod 7, mod 21, they are different, right? These are different residues, mod 21. Okay. All right. So this isn't the only way that you could have done this. You could have also just divided everything by the GCD, including the modulus. And then you could solve the new congruence to get the same exact thing. You could have definitely done it that way. So there's more ways in which you could do this. So there's a couple more examples in the textbook I'm not going to go over, but this is, now you get the idea how this works. Well, maybe, okay, I'll do one more. I'll do one more. So if 10C is congruent to, say, 80 mod 45, then what do I want to do here? Well, I can say the GCD of, say, 10 and 45 is 5. So C is congruent to 8 mod 45 divided by 5, so that's mod 9. But of course I wasn't interested in solutions mod 9, I was interested in solutions mod 45. So mod 9, my solution's just 8, but I get a list mod 45, so I would get 8, 17, just keep adding multiples of 9, so 26, 35, and 44. Mod 45. This is the list. Okay. All right. Of course, if you translated this back into a statement about integers, then you would have, a pretty long list of integers that satisfied this modular equation. Okay. Since each one of these corresponds to an infinite family of integers, right? Okay. So that's how that goes. So now I want to round out this discussion of the basics with just a list of some useful facts. So this is a list of useful things that you can use. Like 3 things you can use to do further computations with congruences. So here we go. So let this following proposition. So let n be a positive integer. Let a and b be integers. If a is congruent to b mod n, then the GCD of a and n is equal to the GCD of b and n. So it's interesting to see why this is the case. So write a is equal to b plus some multiple of n. So a is b plus nk for some k. Okay. Let d be a common divisor of b and n. Well, if d is a common divisor of b and n, it divides both b and n. So it divides b, divides n. So d divides a. So d is a common divisor of b and n. It also must divide a, since I can write a as a linear combination of b and n. So then it divides a and it divides n. So d is a common divisor of a and n. Now, I could have written this same relationship differently. I could have said b is a minus nk. And from that, I could have let d be any common divisor of a and n. And then d would have had to divide b. So the common divisors of a and n is the same set as the common divisors of b and n. So those two sets, the set of all common divisors of a and n and the set of all common divisors of b and n, those are identical as sets, and we just showed that, right? We showed both directions of set inclusion here. Okay. Well, if they're the same set, then they have the same largest element, so they have the same GCD. So GCD of a and n is GCD of b and n. And that's how it goes. All right. So that's neat. So here's an example of how you can use this fact. It's kind of interesting. So suppose you wanted to compute GCD of 1,234 and 10. Well, that has to be the same thing as the GCD of 4 and 10, which is 2, since 1,234 234 is congruent to 4 mod 10. So that's pretty funny, right? This is, in certain instances, you could definitely use this in a clever way to quickly figure out GCDs without having to resort to the Euclidean algorithm or anything like that. Okay. All right. The next bit is a little bit of foreshadowing, and I've already mentioned a little bit that when you consider congruence mod a prime, things are a lot nicer. Things work out a lot nicer for you. For example, worrying about division ceases to become a problem because we already know we can't divide by 0, so dividing by a multiple of the prime p is out. But if you don't have a multiple of the prime p, then any other choice of thing is going to be guaranteed to be relatively prime, so you could always divide by it. Well, if you're familiar with the basic course in algebra, this is saying that if you consider, say, the set of integers, and you're looking at the set of integers congruent mod p, right? So you're not looking at the set of integers now. The set in question is a set of congruence classes mod p. And you start talking about adding these things. Well, that works out nicely, of course. But that is, it turns out that always works out nicely. But even better, if you talk about multiplying these congruence classes, then mod p, I can always divide by any congruence class as long as it's not 0, as long as it's not the 0 congruence class. And so I have two operations, plus and times, and plus behaves really well. Okay, so plus behaves really nicely. And even times behaves really well. So I got a set, and it's equipped with two binary operations, plus and times, and both of them behave really well, okay, rather than just marginally well. So what do you get? Well, you get a field, okay, in this case. You might have thought I was going to say ring here, but I'm defining ring as being times is behaving marginally well versus very well that I get when I have multiplicative inverses. Okay. So anyway, let's do another proposition. If P is prime and A times B is congruent to 0 mod P, then A is congruent to 0 mod P, or B is congruent to 0 mod P. Phrased in more elegant language, what is this saying? This is a statement that if you consider the set of congruence classes mod P with the obvious plus and times, this is an integral domain. Okay, so this is saying that the set of congruence classes mod P is an integral domain. If you're familiar with that terminology, that is what's being said here. Okay, so quick proof of this fact. So AB is congruent to 0 mod P. That means that P divides A times B, but you have a prime, it divides product, so P divides A or P divides B. But hey, that means that A is congruent to 0 mod P, or B is congruent to 0 mod P. So that's it. So you see that some of these congruence statements are actually just a recasting of earlier things that we proved. Okay. One more corollary, which is a corollary of that fact I just proved. So let P be prime. Then x squared is congruent to 1 mod P has only the solutions x is congruent to plus or minus 1 mod P. Both the proposition I just showed that if P is a prime and A times B is congruent to 0 mod P, then either A or B has to be congruent to 0 mod P. Both that and this corollary of this fact are not true in general. Okay, so if you pick M instead of P here, where M is composite, and you look at these things, in general, these facts are not facts anymore. They're just not true in that case. So proof. So x squared is congruent to 1 mod P. That is true if and only if x squared minus 1 is congruent to 0 mod P. Now you see why it's a corollary of that previous fact. If and only if I can factor x minus 1 times x plus 1 is congruent to 0 mod P. And now I am happy. So x is congruent to plus or minus 1 mod P. And those are the only options by that proposition. Okay. All right. Okay. So that is that. Now, that basically sums up all of the basic arithmetic of congruences. This is going to be built on through doing a bunch of different examples and showing some things piece by piece that you get out of this. But in terms of the core of your understanding of how to deal with congruences, this is pretty much it. Now, I know that a lot of this stuff seemed really simple, but even though it's a lot of this stuff is really trivial, some of this stuff was just a restatement of either facts we'd proven earlier or just a restatement of some like definition about divisibility, right? The early stuff we did with congruences was all those proofs were typically like one sentence because it was just really barely even a proof. It was almost true by definition. So it was almost like a relabeling. But even though that's the case, this stuff is really, really important because swapping over to the congruence language allows you to do a lot of computations really, really quickly. So there's actually a ton of stuff you can do in this new world that is almost impossible to do without it, without using this some kind of language that is equivalent to talking about congruence mod n. So that's how this goes. So the rest of this chapter until I get to linear congruences and then the Chinese remainder theorem is actually going to go pretty quick. So the next few sections are going to go pretty quick. So tomorrow I will do modular exponentiation. So that comes next. That's actually a neat process. So I'll do a quick example of that. Divisibility tests, something that you already have experience with from elementary school when you first learned some quick tricks for determining whether or not a given number was divisible by some small number. So I'm only going to do divisibility tests up to up to 11. There's more complicated divisibility tests that you can devise for things, but we'll talk about this as well. And then 6.4 is linear congruences. So this is 6.2, this is 6.3. Linear congruences is 6.4. So we'll spend a decent bit of time on linear congruences, probably one whole lecture on nothing but this linear congruences chapter. And then we'll do the Chinese remainder theorem, and that's the last thing we'll do in chapter 6. So then we'll do Chinese remainder theorem, because that's important for what we're going to do next. So we'll do Chinese remainder theorem, and that will be 6.5. I am assuming that I think how this is going to go is I will so this Tuesday's lecture will be these three, and then Wednesday's lecture will be Chinese remainder theorem and more. So one thing I wanted to say is I went through and added all of the lecture videos to the syllabus page. So if you go to the syllabus page, there's a list with links to every single lecture video, including a description of what I covered during that lecture. And also on YouTube, on the YouTube channel for the course itself, I piled all the videos into a single playlist as well. So I've organized these things a little bit to make the navigation a little bit easier. But anyway, I think that's all I wanted to say for today. So remember, I have office hours at 2. I'll post a reminder announcement when I host those. So same deal as last time. Basically, I will have the stream up. I will be here. Sometimes I'll be away from the computer for a little bit. So type your questions in chat, and I will respond to them quickly. Some I will just answer in chat. Some, I will, if it's a little bit more involved, I'll actually work it out on paper. If you have questions about the exam, you can ask them, but no guarantee that I will be super helpful. But as far as questions about the homework 2 that you still have, I will try to be more helpful with those than I will be for the exam questions. So anyway, that's the plan. So I will see you all at office hours. If I don't see you at office hours, I will see you all tomorrow. So that's it.